Next presentation is solar cells made from thin, high-quality epitaxial silicon foils. Will be given by Dr. Gordon from IMEC. So please, Dr. Gordon.
Thank you for the introduction. First of all, I would like to thank the organizers for giving me this great opportunity to be here today and to give this presentation. So I will talk today about thin, high-quality epitaxial silicon foils, how we can make them and how we can process them into devices. And this work was done at IMEC in Belgium. So first, as a short introduction to the why of this work. So if you look at this cost structure of a crystalline silicon module of today, so this is data taken from the ITRPV roadmap, we see that roughly 1/3 of the cost of the module is directly linked to the cost of the crystalline silicon. So if we can reduce the cost of this crystalline silicon, we immediately also reduce the cost of the module. So that's why, again, a figure from the ITRPV roadmap, it is clear that the industry wants to reduce the thickness. So if you look at this curve in red, within 10 years, the industry wants to go to wafers with a thickness of only 100 micrometers. But you also see on this roadmap from ITRPV a blue curve, which actually goes much below 100 microns, even below 50 microns. So actually the roadmap keeps open the possibility to go even much thinner in the near future. But of course, to be able to do that, there are some problems that need to be tackled. First of all, how can you make a 50 micrometer or even thinner crystalline silicon layer? And secondly, if you have such a very thin layer, it becomes flexible, but it's also very fragile. So you need to have new ways of handling such a very thin material and processing it into a device. So now in the next slide, I will show you the approach that we are developing at IMEC to tackle these issues. And this is based on the use of porous silicon and epitaxy. So I will walk you through the process schematically. So we start with a silicon substrate and we do porous silicon formation. So I will give more details about that later on. After reorganization of this porous silicon, we can actually grow a high-quality crystalline silicon epitaxial layer using thermal CVD on top of this porous silicon. And typically we use 40 micrometers as thickness, but of course you can select the thickness in any way you want, and you can also control very well the doping profile of the material. Then the idea is to process the first side of this epitaxial foil while it is still attached to the parent substrate, and we process this side into the front surface of the device. Then we do a laser scribing process to actually define the exact area that we will lift off, and then we will bond this foil to glass and detach it from the parent substrate. So at this point in time, you have a substrate that you can reuse and can go through this cycle again. And you also have silicon layers on glass, which are already processed on one side and now still need to be processed on the rear side while they are attached to the glass. So in this process, we not only make these epitaxial very thin foils, but we also process them into a device, and we do it in such a way that during the whole process, the foil is always attached to either the parent substrate in the first half of the process or to a glass in the second half of the process. So it's always mechanically stable. So this brings me to the outline. So I have 2 points. In the first point, I will talk about the epitaxial foil quality that we can achieve. And in the second part, I will talk about how we can process them into a device. So first, what about the foil quality? As I've shown you, we actually grow the epitaxial foil on top of porous silicon. And the porous silicon, as was already also shown in one of the previous presentations, is typically made with such a double layer structure. So we use electrochemical etching, and you have a low porosity layer, typically 30% porosity, on top of a high porosity layer. And you have two layers because actually your porous silicon will also have two purposes. The low porosity layer is there as a seed layer for epitaxy, so that's the template on which you will grow. And the high porosity layer is there because you want to detach at some point to foil from your parent substrate. Now, on top of this as-grown porous silicon, we cannot really grow good quality material, so we first have to do a high temperature bake for a short time. So in this high temperature bake reorganizes the porous silicon. So this is the as-deposited porous silicon again. And after a short bake, just before we do the epitaxial deposition, you see that actually both the low porosity and the high porosity silicon completely reorganize. So this is after the reorganization. So what you now see in the low porosity silicon layer, first of all, you have a closed surface. So that's what we need. That will be our surface on which we grow epitaxy. And inside, of course, this layer, you still have a lot of voids. So you have large voids, you have small voids, so you have a mixture of different sizes. The high porosity silicon layer basically becomes more or less one large horizontal void, which we call the detachment layer. So that is the weak layer that will allow detachment of the foil. And of course, the low porosity silicon is still attached to the parent substrate on the sides, not shown here. And also here and there, you still have some small interconnections between both that actually support the low porosity silicon layer. So now we can grow epitaxy on top of that. And then typically we grow N-type material with a thickness of 40 micrometer. And we, of course, if we want to, we could also already grow an emitter or a front or back surface field, so we can tune the doping profile. If you zoom in on this porous silicon area, you see that we have here the parent substrate, this detachment layer, and more or less suspended above that, you see the low porosity silicon layer, and then on top you have the crystalline silicon. So now what about the material quality? So if we think about the material quality, it will be dependent on these three parameters. First of all, of course, it will depend on the quality of the template, the porous silicon template that we have. It will also depend on the epitaxial deposition process itself. And it will also ultimately depend on the detachment process. Because if you think about it, so if we would have to use a lot of force to lift off this foil, we could easily damage it or perhaps even break it. So these are the three main parameters that influence the material quality. And to assess the material quality, we typically do lifetime measurements in this configuration, so using QSPC measurements of the foils when they are passivated on both sides with amorphous silicon and bonded to glass using silicone. So actually this configuration in which we measure the lifetime mimics the configuration that the foil will have in the final device. And so the lifetime is our figure of merit for the material quality. So now I will focus on the effect of the porous silicon template on the epitaxial layer quality. So if you consider, first of all, of course, the surface topography, the surface on which we grow the epitaxy will have a big influence on the material quality. But we also have in this low porosity silicon layer some intrinsic stress. And this intrinsic stress will also affect the growing epitaxial material. And then thirdly again, of course, the ease of detachment can also have an influence. So first, if we focus on the surface topography, if we don't do this reorganization properly, we can have all kinds of defects. For instance, the surface might not be completely closed, and then you have some voids there, which will be very bad for epitaxy. But even if the surface is completely closed, you can still have a wavy surface, and this will also be really bad for epitaxy. So we have to optimize this template, and we found out that one of the most important parameters to have under control is a so-called surface void size. So we have to reduce the surface void size. What does it mean? So if we look again at the cross-section after reorganization, we see that we have a lot of voids in this low porosity silicon. Some of them are very big, some of them are small. But especially if we have a lot of voids close to the surface on which we grow, this will affect the epitaxy. So we have to reduce the number of voids we have close to the surface, and especially also reduce the void size there. If we do that, if we can reduce the surface void size, this will result in smoother templates and will also result in reduced stresses, and this should result in better material quality. Now we have already shown in the past that there is a relatively easy way in reducing this surface void size, and that is actually by reducing the starting low porosity layer thickness. So if we start with a low porosity layer of 730 nanometers, after reorganization we see that we have a lot of large voids close to the surface. If we use a much thinner low porosity layer to start with, we see that of course you have much less material here, so you also have smaller voids there. So if you now grow epitaxy on these three types of materials, you immediately see the following. So you see that you will have much less defects when you grow on top of this material, and this results automatically in a higher lifetime. So in black here you see the lifetime for this sample, which is around 100 microseconds in this case, and in green you see the lifetime for the thinner low porosity layer, which is twice as high, 200 microseconds. So from this picture it is very clear what we should do. We should go to lower or to thinner low porosity layers. But of course life is not, it's never really simple, so there is another effect at play. So we also found out that if we go to thinner low porosity layers, we have more difficult detachment. And detachment is also important. So we don't only need to have good material quality, but we also need to be sure that we can still detach the layers. So this graph shows the detachment yield as a function of the thickness of the low porosity layer. So if we have a very thick low porosity layer of 2 micrometer, we have 100% detachment yield. That means if we want to detach a large area foil, we can do that, and it will work more or less 100% of the time without cracking the foil or causing defects. And the reason for that is clear if you look at the cross-section. In this case, we have this detachment layer, this horizontal void, which is perfectly formed. Now, if we go to thinner low porosity layer thicknesses, we'll have better material quality, as I've shown in the previous slide, but actually our detachment yield will be close to 0. So this means in this case that we will not be able to detach large area foils anymore. We will be able to detach pieces of it, but not completely. And the reason is again very clear if you look at the cross-section in this case. You see here that this large horizontal void is not properly formed anymore. So the thickness of the low porosity layer actually also influences the formation of the detachment layer. So we now have basically 2 situations. On the left-hand side, we have a type of sample which is easy to detach, but where the template is not as good as we could get it. And on the right-hand side, then you have a much better template, but you cannot really detach that anymore. So what we of course want to do is we want to have this template on top of this stack. And actually we can do that by going to so-called triple layer stack. So instead of making a double porous silicon layer stack with high and low porosity, we actually go for a triple layer stack. So what we do is, on top of these 2 standard layers, we introduce a 3rd very low porosity layer. And if we do that under the right conditions, then after reorganization we get the following. We get this horizontal void which is perfectly formed, so defect-free. But now on top of this typical low porosity silicon layer, we have now a very thin region where you have almost no voids anymore. So you still have a lot of large voids here, but they are not very close to the surface on which we grow. So and now if we grow epitaxial on these 2 types of samples, and we look at the lifetime, then in this particular case, we got for the triple layer stack 350 microseconds, and for the standard stack it was around 300 microseconds. So we clearly have an improving lifetime in material quality, but both layers have the same 100% detachment yield. And so in this case, as I showed you, this was one of the first experiments we did like that. You still see we have some voids in this surface zone. But in the meantime, we have been able to create void-free surface zones in 2 ways, by simply optimizing this triple layer concept further. And this allows us to actually create now detachable stacks which have this completely void-free surface zone. So we have a zone here of around 100 nanometers, which is really crystalline silicon with well, almost no holes anymore inside. But we can still make this also a little bit thicker. So we have introduced what I call here a novel type of porous silicon stack, which results in around 300 to 350 nanometers of void-free surface zone. So I cannot really go into detail in what exactly this novel stack is, because we have a patent pending on this. But if we now grow on top of this material, we reach even much higher lifetimes than before. So we have so far reached lifetimes of around 700 microseconds. And of course, combining this with 100% detachment yield, so we can detach these foils without any problems on large area. And 700 microseconds for this N-type material corresponds to a diffusion length of around 900 micrometer, so that is roughly 20 to 25 times the thickness of the layer, which is typically 40 microns. So this should be really good enough to make high efficient devices.